Okay, good morning, everyone. So let's get started with the 6th lecture of the dark matter school. Okay, so today, as well as yesterday, we're gonna continue to cover direct detection of dark matter. So in this time, I will go into the details of the experimental aspects of dark matter direct detection. I'm not an experimentalist, but I will try to share what I know. So what we've seen in the past lecture was just actually driving the scattering rate for dark matter scattering. And at the end of the day, we discussed the Vmin, which is the minimal velocity at which a scattering can take place at a given detector with a given energy threshold. Just to revisit, so to recap, so you have here in this plot is in the y-axis the Vmin, the minimal velocity, and the x-axis the dark matter mass, and take into account the energy thresholds of different direct detection experiments. We notice that xenon detectors. Hold on. Okay, it's appeared. Why do I see this? Okay, you entered. It's appeared. No, it was not. Someone was trying to enter, but okay. So what we're seeing, what we saw was that a xenon detector, or in order to observe a signal, would have to rely for 10 GeV dark matter particle masses, would have to rely on just on dark matter particles that would have a minimum. I'm not sharing this screen. That's what they're complaining about. You're right. Sorry. So if I make something stupid, you can just say, okay? Just, yes. Turn on your mic and just say, hey, Farnell, you're doing something stupid. So share your screen. It's fine. Okay, so now you can all see, I guess. Yes. Okay. So you have I'm gonna go repeat again. So in this plot, you have the minimum velocity as a function of dark matter mass. And in the black curve, you have different curves which represent the minimum velocity which a dark matter particle should possess in order to produce a detectable signal in a given direct detection experiment that features different elements, either xenon, sodium, or germanium. So for xenon detectors, you typically need a minimum velocity much higher than 600 kilometers per second, let's say 10 GeV, right here at this point. So 10 GeV in order to produce, hold on. Why is it? Okay. Sorry. So you see, I would need a minimum velocity larger than 600 kilometers per second in order to produce a detectable signal in a xenon detector, okay? Given the threshold they had at that time. And for germanium, you need a much lower velocity. And that explains why germanium and silicon, for instance, are ideal targets to search for low mass dark matter particles, okay? That's just comes from kinematics. And the fact is, so for instance, you say, how, okay for now, but somehow, if I somehow can really low the threshold of xenon detectors, then xenon detectors can be competitive with germanium and sodium detectors if I really low the threshold for xenon-based detectors. This is true, but it's much harder to low the threshold for xenon-based detectors than for semiconductors such as germanium and silicon. Okay, so this is just experimental fact. Someone tried to enter and gave up. All right. Let's cover something else. There's a blank sheet there. Okay. So let's go into, okay, now, so we are not just discussing the minimum velocity. All these talks are related to the experimental side of dark matter. See, now you can understand now why we need different targets to search for dark matter, because we don't know what the dark matter particle mass is. Therefore, you need really different detectors, different targets, because different targets, they are much better at heavier masses. Some other targets are much better at lower masses. That's why you need a variety of nuclei in the search for dark matter. Okay, so it's for our advantage. They are competitors between themselves because everybody wants to be the best. But okay, some of them are naturally the best for low dark matter, and some of the others are the best for heavy dark matter. Okay. Now let's think of study a bit of the background for direct detection experiments. So we're going to discuss something, a quantity called water equivalent. Does anyone know what water equivalent is? No? Anyone in the back there? Does anyone know what's a water equivalent measurement? Leticia, Lucia, Ana, Guillermo?
I think Lucia is giving lecture.
Ah, yes, Lucia is giving lecture. So Mikael, Luca, does anyone know? No? Okay. So water equivalent is simply a measurement of how deep into the ground your detector is. So as soils are different in a different region of the country and different countries, the way you can compare how deep your detector is underground is by saying, if I had just a ton of water above me, how deep I would be. So for instance, the soils are different in different countries and different states and so on. Because the soils are different, I cannot compare, I'm 1 kilometer underground in Brazil is different than being 1 kilometer underground in Japan and in Canada, in Italy. The soil they have, the ground they have, they are different. So they protect more or less from cosmic ray background. So the cosmic ray from the atmosphere is reaching us. And the reason why direct detection experiments are placed underground is to subtract the cosmic ray flux hitting the detector.
In this case, your equivalent would be a kind of normalization.
Yes,
experimental stuff.
It's a way to normalize, to really know how deep your background, your detector is, and in order to estimate the background flux from cosmic rays.
Is it related to what? Sea level?
What?
Is it related to?
Yeah, sea level. So it's the sea level, sure, but how deep it is, it matters depending on the soil. Okay?
No, but I mean,
Because how efficient is your soil to, let's say if you have rocks, and these rocks have some, geologists will study the rocks, geophysicists will study the rocks between you and the surface of the detector. They say, look, according to these rocks are made of these minerals, whatever.
It's like a shielding unit.
It's a shielding unit. So now, okay, according to this place where I am, it would be the same. The cosmic rays that I measure in my lab would be the same of being 1 kilometer below water. Okay? So maybe mine is 2 kilometers underground. But maybe because of the rocks, it's not really 2 kilometers, it's maybe just 1 kilometer. But maybe in the different rocks are more efficient, then I'm just 1 kilometer below the surface. But since the rocks are made of something which are very efficient shielding, then it's equivalent to me be 2 kilometers underwater. So it can be both ways. Make sense? Okay, so you can see here is the muon flux measured at different kilometer water equivalent. Here it is. Water equivalent distances. So as you see, the deepest underground detectors are located at Snow Lab in Canada, and this is the Grand Sasso laboratory. Where it is? Yes. And you have other ones, but these ones are not really for dark matter purposes. So that's the Sudan is another one, and you have many. Okay. Jinping is this one is I believe is in China. Jinping is in China. So you see how deep kilometers underground they are. So it's like 6 kilometer water equivalent underground. Can you imagine how deep this is? And just to have an idea of, for instance, these are the examples of where dark matter detectors are located. So you have this LNGS is Gran Sasso Laboratory, which is the one I showed you. This is the Gran Sasso. It's one of the most famous ones. And this one I visited. And this one is No Lab. I never visited in Canada. This one is the SURF, Sanford Underground Facility. I also visited. It's in South Dakota in the US. So I visited. It's quite amazing. Okay, so Jinping is in China. Now let me show you. So we have a dark matter detector located here. Okay, and we do have a dark matter detector located here, and one here, and one here. The other ones, yes, we used to have one detector here, but then they moved the entire detector to this place. And then later they moved the entire detector to this place because they wanted to move further and further below to suppress more and more the background from cosmic rays. So moving, let's say, a detector of 100 kilograms. So it's not that big, but still. So moving from one country to the other. Now I want to show you some things so you can have an idea, because this is much more cooler than just tell you. So that's the entrance of the Gran Sasso Laboratory. So it's a tunnel that crosses one city to the other in direction of Rome, the city in Italy. And there is a curve where you go INFN, which is the Gran Sasso Laboratory. I'm not going to show everything, otherwise it's going to take quite some time. I'm just going to skip ahead. Look. Look, now I'm going to show you this size. Okay, let me see if I can speed slow. How big this thing is. Look, that's the place where the xenon detector is. See the size? It's pretty amazing. Now I'm gonna see. So those are the photon multipliers. This is the gas, xenon gas. Look, it's pretty amazing. You visited one of those places. It's gigantic. The wiring and see everything. This is to measure a recoil signal. I mean, it's pretty fantastic. That's direct detection, yes. Let's see if there's something else extra. Because there's a moment where, okay, but this one is enough.
Now that you showed the xenon detector, I don't remember the expression for the minimum velocity, but the graph, they are all related to the minerals. I mean, the material. Are they all the same size, or they have different sizes? And even though they have the same for the same, for different sizes, they have the same.
So it matters the mass of the nucleus, not the size of the detector. But the size of the detector, how much you have, you will increase the chances of measuring scattering. Remember, the DRDE depends on the number of targets you have per kilogram. So the more targets I have, the higher is the rate. Okay?
So suppose we have, I don't know, 200 GeV per month. So this is a very different particle than anything that we knew. So in what sense the background is going to get us confused about possible signal?
Okay, he's asking about the background. Let's discuss the background later. Okay, I'm gonna cover this later. So so this is the photo of the background. So this is the Gran Sasso lab, and the thing you saw on the road is under that mountain. So the direct detection experiments is right underground that mountain. And there is a road which goes through that mountain and comes out on the other side of the mountain. Okay? And now let me show you this one. And this is no lab. In Canada. So this they're showing that is the velocity of someone entering the elevator and going down below 2 kilometers. Okay, this is how fast they go. And then that's the path they take to reach the lab. Okay. And those guys are scientists, okay? Are scientists, it's not security people, they are scientists. They're coming from home and going to the lab this way. So 1.4 kilometer walking to reach the lab. And now, before they reach really the lab station, they have to wash up their shoes. They wash them, and then later they have to change their clothes. I'm gonna show it. So see, they have to change their clothes and take a shower because there should be no impurity inside the lab whatsoever. Every day. Okay. So see, it's just showing that they need to take a shower. It's good that there's nobody smelling there. Okay. So then everybody has a name. So those are scientists. You have to wear security equipment. So this is like the lab looks like. Yes, there's cleaning materials and so on. Oh, that was the tank. Well, yeah, this whole thing is the tank. See, those are the walls. They're really analyzing the data. So for instance, the experiment they show is neutrinos less double beta decay. Searching for neutrinos less the double beta decay. You don't know what this is, but it's just searching for is an experiment that tries to assess whether neutrinos are Majorana particle or Dirac particle. Because at this lab, there is not just dark matter, there's other things. There are people doing biology tests, chemistry tests of the soil, testing live plants deep in the water.
What's the name of the particular?
This one super CDMS. And okay, and then after they leave, they, for instance, if they want to get close to where the detector is, there is a vaporizer that, I mean, removes all the dust and small molecules of anything that you have in your clothes when you try to reach close to the detector. So there should be nothing close, any of sign of dust whatsoever in your body when you reach close to the detector. And this is just showing that since they are 2,000 kilometers, 2 kilometers underground, it's hard to have water, clean water. So they have a special pipeline to provide waters to people 2 kilometers underground. And there is a whole purification of water going from the soil closer to the surface down there. And that's what they're showing this video right now. And it's also, there is, for instance, once I mentioned this some time ago, that was impressive to me when I visited not this one in Canada, but the one in the US, in South Dakota, is they had, which is also nearly 1.5, 1.2 kilometers underground. And they had an internet that was in 2013, I think. Yes, 2014 when I visited. And they had an internet already of close to 1 gigabyte. In 2014, 1 gigabyte. Today we have, people are trying to selling 500 megabytes of data and so on. So in 2014, 1 kilometer underground, they had 1 gigabyte. Imagine the wiring of, so that's how I was kidding when I think, hey, when I go, my router is in my kitchen there when I lived. When I go to the to the living room, the internet's not really good. So these guys are 1 kilometer underground, and the internet looks is amazing. I mean, it's crazy. So that's what the place looks like. Oh, look. So this is PICO and Super CDMS. PICO is a direct detection experiment as well. Deep, another direct detection experiment, looking for spin-dependent scattering. And then they have to return home the whole day.
Like daily thing of following.
And now I just want to show you this video because then I'm gonna cover the LUX, LZ, dark matter. LUX, hold on, LUX. What's LZ is okay, this one. I'm gonna explain to you. Oh, there we go. So as you can see, the real detector is just this tank. But there is 1 ton of xenon in this tank. Just to have an idea, purified xenon is so rare that they extract from the surface, and it's really rare. When there is a new detector experiment approved to be funded, the prices of xenon in the market increases a lot. Just because it's so rare, the whole demand of xenon is basically given by dark matter scientists. So they control the stock market, and they also make profit out of that. So they buy people who have experience in the stock market to to take advantage of the situation. Okay. So as you see, I'm gonna revisit this later. So you have a dark matter particle that comes in, hits the target, the xenon nucleus, In this case, we produce a light and so on. But I'll stop right there because I'm going to come back to this video. Okay. So in the end, the main message here so far is that to show you that in order to search for dark matter, you have to build detectors underground or using direct detection through scatterings, nuclear scatterings. You have to have detectors underground because the flux of muons, cosmic ray muons, is so large that you have to really be underground. And the reason is because the deeper you go, the smaller is the flux. As you can see, it goes from 10 to minus 7, 10 to minus 8, 10 to minus 10. And the fact is makes your life easier in one way, because imagine I'm trying to search for dark matter signals, which are rare. They happen not very often. But if there is a 10 to 7, 10 to 8 million flux of muons arriving, it's hard to find few events out of a million. So you have to really suppress the muon flux to have a better handle to really count the events and say, okay, it was not 1 million, was 1 million plus 2. And I need to have a very strong statistical evidence to infer that if I observe a flux or an excess of events or not. Okay, I need to make sure that I observe an excess of events compared to the background events. In order to do so, I need to make sure first that the cosmic ray flux, which is the largest one, is suppressed. Okay, that's the largest background that is. It's not the toughest, but it's the largest. Okay, I showed the video. And see here it is at the Gran Sasso. So you are, that's that mountain you saw. And so for instance, you have Gerda. Gerda is a neutralizable beta decay experiment. CRAS is a direct detection experiment searching for spin dependent. You're gonna learn this soon enough. Dark side is there is a Brazilian woman involved, Ivona Albuquerque. She's a member of this dark side experiment. This xenon, Borg xenon is also neutralizable beta decay. Opera was a very old detector which apparently proved at that time the neutrinos would speed faster than light. And then they made a mistake in the calculation and so on. The project was tanked. Okay, so you made a mistake. You claim that neutrinos have a velocity speeder than the light. And then it was just a mistake when it came out. But people that advocate for Lorentz violation were like, wow, see, we observed that there is violation of Lorentz symmetries in the universe. Opera proved it. And then later on, we realized that they just made a mistake. So, yeah, so we're going to cover this later. Maybe I will, because I'm not sure if I'll have time to cover all that. Okay, does anyone have a question?
Is this DAMA direct detection experiment which measured the signal?
They measured modulation.
Modulation, yes. But it's different from the other experiment you said about it, I think.
Which one? Dark side?
No, other. That also find a signal.
Cosino.
Cosino. Yes.
Yeah, it's different. But it had the same purpose, had the same target, which was sodium iodine, but it did not measure modulation. Cosine, but it's the same idea. Okay. Cosine was made to claim whether DAMA was correct or not.
Okay.
Okay, so and CERN goes in that direction. Rome, you can see there, and so on. But that's I have an idea. So that's a picture of the xenon detector. No, that's not xenon. So this is one is I believe is crest or deep. The xenon looks different. So the supercilium mass. So you see here there are 2 kilometers underground, and that's the picture you saw right from the lab. This one. That's the one. This one here. And now let's go into the details. So the types of readout techniques. I just wrote a text. The types of readout techniques. So what you have is you have different dark matter detectors, and they measure the signals in a different way. So some of them rely on phonons and heat, some others on charge or ionization. and some others on light, which is related to ionization, but it's just measuring light. And I'm gonna show you this video here. Hopefully, yeah, this one. Let me show you what phonos are. This one. Does anyone know? No? Yeah, it's vibrations. So here it is. So it happens is if you have a semiconductor such as silicon or germanium, they are like in a lattice, and when something bumps into them, into an atom, that atom vibrates, and that vibrates the whole chain of atoms. This vibration induces the particle that is a messenger of vibration in the lattice is called phonos. Not really a particle, but it's just the way it is treated, okay? But when this lattice of atoms vibrate, they heat up, and they increase the temperature of the lattice. And then you measure this decrease in temperature. So, okay, so you have a lattice, which something hits the lattice, they vibrate, this vibration increases the temperature, and then it produces heat, and you measure the increase in temperature of the lattice. So it's called heat or phonos, okay, which is what I was showing you before. Yeah, phonos or heat. Okay, and you have also other ones such as ionization. So ionization is easy, everybody knows. It's simply you have an atom with an electron, and then it comes something and it strips off the electron, and you ionize the nucleus, right? So now you have an ionized nucleus. Okay? And ionization is related to how many electrons you stripped off from the atom. Okay? The more electrons I scatter off the nucleus, then the larger is the ionization signal. So ionization is just amount of charge. And scintillation is when these electrons are submitted to an electric field. Let's say the electric field is pointing downwards, E. Then the electron will move upwards. Then since the electric field produces a force, which is the electric force, accelerates the electrons, charged particles, when they are accelerated, they emit radiation. This radiation is light. So you have phonons, ionization, and scintillation, which is the light coming from the fact that you drift the particles upwards or downwards, whatever your electric field is pointing to. Okay? Sounds good? So those are the three main called readout techniques. So is there any question so far? Okay, so, and here is just saying some of the detectors, what kind of techniques they use. As you're gonna see, all of them they are based on two techniques, and you're gonna see it why. You're gonna understand why all direct detection experiments today, they use two techniques. That was not used to be the case before. So some time ago, some detectors use just one technique, and you're gonna learn why this has changed. So, for instance, lux, xenon, that's the ones I'm gonna cover soon enough. And these are xenon and lux are, they are scintillators, okay? Xenon is simply that gas. When you have for instance, when you play Need for Speed video game, have you played Need for Speed? Yeah. Okay. And then you can also have some, that neon light under the car, or maybe in the headlights. So that headlights, that's it's not the xenon I'm talking about, but it's the same effect, okay? Because xenon would be too expensive. It's just when that gas fills an electric current, emits light. So that's what it is. So that lightning comes from scintillators. So, and you have, this is for xenon detectors. They usually rely on scintillation and ionization, these two. And you have semiconductors. Semiconductors, they rely usually on ionization and heat. Okay? And some others which are very different, such as CRAS, which is basically the only one, relies just on scintillation and phonons, which is much harder to have this type of detectors. They didn't prove to be very efficient when you use these two techniques. Anyways, as you see, there are still some detectors here that use just one. See? They're just relying on one technique only. So gamma is old, X-mass is old, deep is still ongoing, but you're going to see why deep is still effective. Pure is gone, pico is gone, and simple is gone. So the only one that survives is deep. Okay, so let's understand why. So in the around 2010, there was a detector called Cogent that was made of germanium, okay, only. And that detector, which is the size of, as you can see, how small it is. And then you see them there, sitting there on plates. And let me explain what this germanium looks like, this detector looks like. Looks like this. So what happened is you have a WIMP or any dark matter particle or any weakly interacting massive particle comes in, hits a germanium target. Well, if the energy of the dark matter particle is larger than the ionization energy of germanium, then you rip off one electron. Okay, that electron, the electric field is pointing upwards, so the electron goes down. Okay, and then once the electron hits down, that is a material here below, which is a semiconductor, which the energy gap between the valence band and the conduction band is tiny enough so that any electron that comes from there will produce a current. Okay? And then I measure that current. So by measuring a current, I actually know what is the energy of the incoming particle in the first place. Okay? Fine? All right. I was gonna throw something at Jacinto because he was falling asleep. All right, so those are semiconductors. Semiconductors rely on ionization. That's you can see, right? But however, it's not, you cannot see from this picture, but it's also when this particle comes, these germaniums are in a lattice, comes, hits one atom, all atoms vibrate, and this vibrate, and again, there is something called here. So actually my figure was right on top. It was supposed to be here, see? My figure for some reason was just in front of it. Where they measure the increasing temperature of the lattice of the detector.
So for a single spectrum, the bigger the better, right? Because you have more agents. But if you rely on heating lattice, a big experiment is going to be like conversely effective, or always the bigger the better.
No. So the bigger the better, period.
Okay.
The point is to have semiconductors in a scale as of 1 ton is not just feasible. Okay. You cannot have like an electronic material made of with 1 ton kilo. I mean, it's just not feasible. Liquid of 1 ton, yeah, fine. But not made of electronics. Semiconductors of 1 ton. It's just not cost effective. You know? So, okay, fine. So he was just asking if I could make it these semiconductors as huge. Yes, but would not be as cost effective because you have to do things, it's non-trivial. So for instance, now you have a huge lattice of atoms. and you have to make sure that you measure precisely the increasing temperature of the whole thing. Right? Okay. So that's for instance, detectors that rely on this, on these measuring the heat and the ionization, which are semiconductors such as CDMS or super CDMS today, which is a upgraded version of the CDMS. Is called dark matter detector and Edelweiss. Edelweiss, I think, is no longer operational. Okay, and that was in 2010. Okay, so far so good. So look at the size. So this thing here, so that's how this pixel there is sort of how they would see each of those lines here, you can see here this thing, is how they can pick up the temperature at even given point of this detector. Somehow they measure the temperature in each part of this detector. And remember, this detector is the size of a cell phone, basically. And here's the picture again. So if I have a dark matter particle comes in here, strips off an electron if it has enough energy, and then the electron field is drifted downwards, then the electron goes upwards, and then electron goes up there, here, if it was an electron, and then you have they call it a hole, right? In solid state physics, you interpret it as a hole going upwards. Okay, fine. And so as you can see, these detectors is limited by the energy. So in order to see a signal, if I use germanium is a semiconductor. So basically, in order for me to see a signal, which is ripping off an electron, the energy of the dark matter particle has to be larger than the excitation energy of the germanium, right? Because if I don't rip off an electron, the only thing I could see in principle would be the vibration of the lattice, but this one is harder to detect for experimental reasons. So really the ionization of the material is the one that dictates the energy threshold of the detector, okay? So the larger the energy gap, the better for low dark matter masses, because I need lower thresholds, remember? Because the lighter the dark matter mass, the smaller is the energy. Remember, energy is proportional to the mass. So the smaller the mass, the smaller the energy that the dark matter particle will deposit in your nucleus. So then I need a target which has a very small excitation energy. Okay, or ionization energy. And here's a picture of the detector itself. So that thing here, in this place here, this hole is where those detectors would be, these ones, okay? Okay, and let me tell you a story very important for direct dark matter detection. So as I said, so you have a dark matter particle comes in, the one in black, hits a germanium, strips off an electron, I'm assuming it had enough energy, and the electron, if the electron field is pointing upwards, the electron goes downwards, or vice versa. Okay, fine. And then, as I said, there's a semiconductor here upwards or below, and when the energy gets, the electron gets there, goes to the conduction band, produces a current, and measures the current, then I can infer the energy of the incoming particle in the first place, okay? Okay, so what Cogent decided to do was, look, it's really hard to measure energy just using phonons. The vibration they produce is really hard to pick up. However, since back then, people said, look, but it's always good to have two readouts techniques. Why? Because if you had a neutron, the neutron will come in. It does not interact strongly with the electron. Neutron has the interaction between a neutral particle and the electron will produce simply, let's say, we just hit the neutron. That comes from simulations, okay? So you have an atom, proton, and electron, let's say in hydrogen. A neutron particle comes in, just smashes the proton vibrates, and the whole lattice will vibrate and produce phonons, a large phonon signal. Okay? If there is a charged particle, electric charged particle, comes in, we'll do the same, but plus we interact strongly with the electron because it has electric charge. So you have electromagnetic interactions, right? Then you'll have a large phonon and also a large ionization signal. So if it's a neutron-like particle, it's more just vibration. If it's a charged particle, it produces both in large amounts. Okay? So it would be a way to distinguish a neutral incoming particle from a charged incoming particle. Yes. Okay? Fine. But what they decided to do was, look, it's really hard to pick up phonon signals at small energies, so I'm going to drop the whole phonon measurement and just rely on ionization only. They decided to do that. I will not pick up any phonon. Forget it. I'll drop it. Why? Because then, since my semiconductor has a very small energy gap, I can measure really low dark matter masses, because even low dark matter mass will produce an energy which is sufficient to ionize the germanium. I don't care about the phonon signal. And people said, okay, and how do you know it was not a charged particle then? How can you distinguish now if it was a charged particle, was a neutral particle? I said, no, but we have a very good estimation of the background. I know how many neutrons will come from the rocks. I know how many neutrons will come produced from cosmic rays, whatever. So there'll be no, I'll know how many events exactly I'm going to get from background, from neutral particles. Then I'm going to rely on charged particles. Yeah, please. And that's what they did. What they saw an excess of events of particles. Okay. And before that, I'm gonna show you what they saw. So here's the figure from the original paper. That's the reference right there. This one, 1002. So from February 2010. So this figure here, what you see is the following. So here they say, look, if there are some backgrounds from M gamma. So if there's a gamma particle, a photon comes in, we'll produce a signal in red. This one right here. If there is an electron coming in, I'll see this band right there. So there's a distribution. If there's if a gamma or an electron coming in, I know where they look like. But you see, there are not many events in the middle. Okay? Fine. And what they realized, what they claimed. Now I'm gonna go back. The claim was the following. Look, I know that I simulated if a neutron, because everything goes from simulations, for instance, calibration. I take a neutron source and hit my target. And then I see how my target reacts. Okay, so there's a neutral particle, then I know how my detector reacts. If there's a charged particle source, how it detects, how it reacts. If there's a gamma particle, I know how it reacts. And then from that, I calibrate to distinguish a charged particle from a neutral particle, just seeing how my detector reacts at given energies. Okay, that's what they do. Fine. Then they did observe an excess of events at low energies, which were not consistent with electric charge particles. And the events they observed was much higher than the number of events they expected from neutron-like particles. So they said, their claim was, we observe an excess of events which is not consistent with a neutron-like particle. That was a claim. They didn't claim they observed dark matter. They said, the excess of events we observe is not consistent with neutron-like particles. Okay? Okay. And then that comes something to mind that you're gonna learn right now why dark matter experiments discuss, direct detection experiments discuss something called fiducial volume. You're gonna learn this is why. So people started realize that if you have a detector, let's say a cylinder like this one, I know the electric field should drift upwards, okay? It's pointing upwards. However, because these things are made of electronics materials and they produce electric fields, for some reason, at the surface of the detectors, the electric field is not fully like pointing upwards. There's some small deviations towards the surface.
But it's what we call the boundary effects. Like in all the experiments that you realize with electric fields, like in physics, in the undergrad classes, you have problems with the electric field in
the surface?
Yes.
Okay.
Opposed to the boundaries.
Yeah. Okay. I didn't know. And then they had the electric fields, and some of the detectors, they do have electric fields right there. They install electric field sources around here in the surface. Anyways, so let's say I had just the figure in black, a cylinder, and an electron comes in here, and then it's drifted upwards. However, how I'm going to distinguish if a neutron comes in right here, induces a beta decay, okay? Okay, one is a proton, so it will be shifted in a different direction. But there also comes an electron, and the electron appears right there. Okay, right at the surface. However, this electron is there, so I see the proton, and then you can say, well, it's not dark matter because I saw a proton as well. Then you can distinguish the one from the just something neutral comes in into the whole detector and produces just the electron. In the other case, you produce an electron and a proton, right? But the point is, because of this electric field not being fully constant or like pointing towards upwards or downwards or whatever, in the corner at the surface, these surface events, this surface region induces the production of other charged particles. So when the neutron comes in, this electron field, you can have, for instance, this E, for instance, this is an electric field. E, that's the proton decay, the neutron decay, right? Right? That's the neutron decay, fine. But then I can have this one. Right?
Yes.
And this would be this one.
Or in this case, it could be opposed.
Or, no, but I have to conserve baryon number.
Okay, it's already opposed.
Right? So, and I can also have this one.
Electron.
And then I have an electron here. And I can also have this one. Right? No, there's something wrong.
Neutrino should be anti-neutrino.
No, neutrino should be neutrino. Baryon number, baryon number.
But I mean the last process.
The what? Which one?
The last one.
This one?
Yes.
Yes, should be anti-neutrino. Well done. And this one, I have a baryon number. I should have a baryon number, right? I have an electron. If I have an electron here, I should have a positron here. And a neutrino. I mean, what I'm trying to say is I can play around with the beta decay the way I want. So what your claim is, I can have a neutron come here, find an electron from this thing, or a proton from the nucleus, and produce electrons from there in this surface. And it would be hard for them to distinguish the electron produced from the surface events from the electrons produced from the nuclear recoil. Okay? And since the electric field at the surface is not linear, then for them it's harder to distinguish whether this electron was coming from a neutron like particle or from some from beta decay or from beta related processes than from just nuclear recoil. Okay? And that's what Cogent did. Said the claim was, look, fine, okay, we can have all that. So what I'm gonna do is I'm gonna now require that all the events in the surface will be rejected from my analysis. So I'm gonna just take the cylinder, the inner cylinder, and this volume now I call fiducial volume.
This concept is exactly as in the collider says, about fiducial cross-section.
But it's not the same.
I mean, about you have you're entirely probing space is not exactly the entire.
The full space, I know, but this is but I know it's not the same.
But it's the same
meaning.
idea.
Yeah, it's the same idea. So okay. So fiducial means that you're not taking the whole space phase or the whole volume. Okay, that's what it's just taking a smaller amount. What you could have do in principle. So I had the whole volume, but I took a smaller volume to avoid surface events. Because they calibrate, so they're calibrating, right? And then they realize that if events happens around here, they cannot really make sure distinguish background from signal sources.
So in this case, if I would put some, I don't know why, but I would put some constraints on my theory about the density or the volume, I should take the fiducial
volume. So you should take the fiducial volume into account. So when we had that scattering cross section, this one, the scattering rate, this one. Where it is? Yeah. So these number of targets we adjust for the fiducial volume. Number of targets per kilogram. Okay? You're just gonna take into account the fiducial volume.
Those interactions they are detected in the bases.
Mm-hmm.
But this volume it considers the interaction between a neutron and the bases as well.
Mm-hmm.
Because they have a technology. It's called shielding. So in some of this, in the entire experiment, you have a kind of shielding to avoid the particles that comes from outside, but also you take out.
Yeah, but the shielding is effective. So he's asking about the shielding. Shielding is effective for charged particle sources. It's called muon veto. So what happened is, this is a detector, so that's the cylinder. Surrounding the cylinder, which is the video you saw, the detector was just something small. There was something much bigger around it. So one of those things, you use a plastic scintillator, because any charged particle, when it passes through a plastic scintillator, will shine. In this way, what they do is the following. They have when there's a muon, let's say a muon surface from the cosmic ray muon passes, and they say, okay, if an event happens within, I don't know, something seconds, reject it, because a muon passed. They detect the charged particle. So it's a muon veto. So it's surrounding the whole detector. The non-charged particle, the only way you can assess this is by calibration. You have to estimate through calibration and knowing the rocks and so on, and having a prototype detector and detecting what's they call R&D phase, research and development phase of any detector that is, without not being dark matter, any detector has this phase, which is just a prototype, and measuring throughout the year or more years how many neutron events, induced events they detect. And then they measure, wow, this year should not be very different from next year and then the other year. So I have an estimate of the average, right? So you don't have a time-dependent source, neutron source is maybe is rare, right, to have. Just 1 year, they pick to have some beta decay just in that year, and it's assumed to be smooth. So once you measure the neutron-induced sources, background sources, then I have the number. Now I place my whole detector and the mu veto. So how many background events do you estimate? Well, it's the one that I measured in the R&D phase. I should expect this number of events. They will be there regardless of what you do, because you cannot avoid them. What the best you can do is just take the fiducial volume to avoid the surface events and see what happens. If it's a muon passes, you reject the event. If there's any dark matter signal happening right at the same time, forget it. You remove it anyways. Just take fiducial volume, and that's you see what happens. So the number of events you detect is the total number of events. If the total number of events you observe matches the one you measure from neutron-induced sources, there is no excess of events. Okay? So there is no signal to be reported within the error bars. Okay? Okay, so now you now understand why all detectors have a fiducial volume to avoid surface events. And so in that year, Cogent claimed to observe some excess of events. And they said, look, I have two interpretations for this excess of events. It may be something that's not standard model physics, but assuming it is, I can place a limit on the scattering cross-section if it is dark matter. So I'm assuming what I saw was just consistent with the background. Okay, and then they place a limit. That's the limit from the original paper. This one in blue. As you see, is much weaker than other limits. So for instance, this one for lower masses would be the best. So the other limit at that time was this one. You can see here in purple. This one is from xenon 10. It's a xenon detector with 10 kilograms of xenon 10. But see, they go to lower masses. And then they claimed to reject the signal from the background, claiming the following. If there is by any chance a neutron, there is a neutron coming and hits my germanium target, as the neutron, for some reason, they have a neutron source, they calibrated, they realized that the neutron takes some time. The electron stripped off from when the neutron hit it, the target, would take some time. But the events they observed took much faster time to reach the semiconductors where they would measure the current. So they were claiming, look, there is no neutron source we know around in our place that could produce such a large energy. And the neutron has a mass of 900 something, 1 GeV, 938. 1 GeV. What I'm seeing it is producing an energy much larger than 1 GeV. The corresponding mass is much larger than 1 GeV. And we don't know any neutral particle in the standard model that has a mass much larger than 1 GeV. So I'm claiming whatever it is, maybe is beyond the standard model physics. If this is true, so this time it takes for the charged particle to reach is called rise time. So how time it takes for the electron to rise and reach the surface. Okay, if that is true, so this, as you can see here in this figure, that's the events they measured, the one in blue. And the one in black is if you had a dark matter particle with a mass of nearly 7 GeV with some scattering cross-section at 10⁻⁴ picobarns. As you see, it matches really well the data. Okay, really well. Okay. And they plotted, if it is dark matter, what should be the scattering cross-section and the mass that best fit the data? Which data? This one in blue. And they measure this one. So those are the best fit regions. Okay, so you should have a cross-section of around 10 to minus 4 picobarns and mass of between 8 and 10 GeV, 12 GeV or so. And look at the limit. Look how it is. So the best fit region to explain the cogent limit is this one here. And this one in dashed is the limit from xenon collaboration. So xenon is already cutting almost half of the parameter space that could explain the signal if it is dark matter. But then people start diving into things, because once you see a signal, you start to revisit all the assumptions you made the whole thing for the whole history of direct detection experiments. And then they realize, we had an important lesson, this fiducial volume. The second lesson, now you're gonna see is this L effective. It has to do with the luminosity effective, or the efficiency at which the detector can observe a signal. And you're gonna explain this. So it's the following. My energy threshold, when I say that my energy threshold is the energy at which below that I can't see anything, it's not something like solid. So if my energy threshold is 5 eV, I'm just picking them, 10 eV, 10. If a particle comes with 8 eV, can I see it or not? Yes, you're gonna see it, but with less confidence, right? If it's 12, yes, I see it with a certain confidence level. So there is, when I say the energy threshold is something, it means that something is just related to some confidence level at which you can see a signal or not. Okay? And when the word claim is that what the efficiency, the threshold that xenon used was not a 95% confidence level on the threshold. Okay, was a 68%. So it's not so good. So let's say if I force that you need a 95 confidence level that you detect or not, then your constraints weakens, because you need to be sure. That's why their curve, which was this one in dash, moved up here. And if you move up there, then the whole region is consistent now. Okay? So now you're going to see from that moment on in the history of dark matter searches, all dark matter papers from experimental collaborations have a plot saying what's the efficiency as a function of the energy threshold. All of them have this paper, has this. So before they didn't. Now they have to show it, because we need to know how confident they are of having a given energy threshold. Okay? So this is lesson number 2. And at the end of the day, there's a third lesson. So this thing is really related to something called, also, this is the second lesson. So it's experimentally speaking, how well you know the luminosity, or for instance, the energy, how well you can discriminate whether you saw a signal or not. And the other one is called quenching factor. So what is quenching factor? Quenching factor here, or Q, quenching factor, is the relation between the recoil energy, nuclear recoil energy, and the ionization energy. Because remember, this is easy to understand. The particle comes, it strips off an electron. The electron grows up and then produces a current. From that current, I know how many electrons were drifted. So I measure the number of charge. But to relate the number of charge to the nuclear recoil is something else. Why? The dark matter particle comes with some energy. Let's say 10 eV. 10 eV. Part of that energy will be converted to strip off electrons. The other part of the energy will maybe be converted to vibrate the lattice. So how much was converted to vibrate the lattice and how much was converted into strip of electrons? You don't know. So what you have to do is calibrate your detector with a neutron particle, which is doesn't have charge, and see how your detector responds and says, if the mass is this something, if a neutral particle comes with 1 GeV of energy, I measure this amount of electrons and I measure this amount of vibration. If 10 GeV, this amount of electrons, this amount of vibration. Then I know if I measure this amount of electrons, what's the corresponding total energy that came in the first place, which was deposited, which is called nuclear recoil energy. Okay? Because the total energy is not into ionization only, it can be to something else. So this ratio between the total and the one that goes into ionization is called quenching factor. That's the ratio of the energies. Okay? Fine? All right. So usually they divide in Q like this. They call E ionization is the opposite over E recoil.
I think someone's asked something.
No idea. So I'm just saying no. I think it's when I asked about what I asked about something else, right? Yeah, the water equivalent. Okay. She finished there. Okay? Fine. We learned what a quenching factor is. And now you see now all papers have this quenching factor result in their papers. So just be careful with the quenching factor. With my quenching factor. Why is that? Because you're gonna see, and today there is a battle between the Chinese and the Europeans. Why is that? Because you're gonna see a signal. I'm gonna cover this later. There is a signal that goes like this: mass and cross section. And there's a battle. For instance, let's say battle in a good way. Okay, there's a limit from here from one collaboration. I will not even put the names because this is recorded. One collaboration comes, that's the limit right there. And there is another collaboration that comes, say, hey, my limit is better than yours at low energies. Like this. That's collaboration 2. Okay? So remember, everything above is excluded. So if mine is below yours, mine is better. And they say, hey, wait, okay, fine. But tell me what. That's towards lower masses, right? So that's when the really quenching factor is irrelevant because remember, let's say if the quenching factor is 1, then if I measure some amount of electrons, I know exactly what was the energy, right? Recoil. But as I'm dropping the energy of the dark matter, or dropping the mass of the dark matter particle, dropping the energy, reaches a point where near where my energy threshold is. So at the near the threshold, what is the confidence level at which you know how to observe a signal? And it's around there where it's really important to know precisely the quenching factor, right? Because let's say if the quenching factor is 1 and my energy threshold is 10 eV, if I measure 10 eV, the energy recoil is 10 eV. But if it was 9 eV, then I can't see it, right? Because my energy threshold is 10. Was below my energy threshold. I could not see it. But if my quenching factor was not 1, I could not even see it before. If my quenching factor is 0.1, if I observe 10 eV, I don't see anything. It's already below my energy threshold. Remember, energy quenching factor is energy of ionization over energy nuclear recoil. So if my energy threshold is 10 eV, okay? That's my E threshold, 10 eV. Then if I measure something, that's the energy threshold, okay? This energy threshold is related to this one. This one here. the one that I really measure. I don't measure recoil energy. What I measure is the amount of electrons or the amount of vibration. That's what I measure. I do not know the energy recoil. I can convert to what I saw back into energy recoil, right? I don't measure energy recoil. Okay, so I say, okay, I need to measure ionization energy of 10 eV. And then if I measure 10 eV here, and the energy recoil, the quenching factor is equal 1. So let me just rewrite the equation like this. Energy nuclear recoil is 10 times, Q equal E ionization, E nuclear recoil, just E. And ionization is Q times E nuclear recoil. So let's do it. So I'm comparing different detectors. So Jacinto has a detector which the energy of ionization energy has to be larger than 10 eV. Okay? And Ricardo has a detector which the energy, ionization energy, should be larger than 15 eV. Okay? So suppose Jacinto is better. But they are made of different detectors, made of different materials. So they have different quenching factors. Okay? The relation between what the total energy that gets in and how much is distributed in different ways is different because these are different detectors. As you already from this, I don't even need to plug in the numbers. You already know that if I measure 10 eV of ionization, and I say I cannot is different from saying that Jacinto or Ricardo observed 10 eV of ionization because we are made of different things. Maybe he's sensitive to a different energy recoil. You're sensitive to a different energy recoil, and I'm sensitive to a different energy recoil. If we measure different energy recoils, means that the dark matter mass we measure are different. So we are sensitive to different dark matter masses.
For the same ionization energy.
For the same ionization energy, because I have different quenching factors. But if we are made of the same material, the same germanium, the same silicon, the same xenon, then we all should have the same quenching factor. Well, if your hard electronics are all good, the same. See? So when one detector, such as Cogent made of germanium, observes something, and xenon did not observe, which was made of a different target, and say, okay, what was the ionization energy you observed? Mine was 10. I can also see 10 eV of electron for ionization, but I did not see anything. So what? The way the total energy is distributed for different targets is different. So it doesn't mean, again, that your case, for instance, 10 eV maybe corresponds to 10 GeV dark matter. 10 eV ionization corresponds to 10 GeV dark matter. Maybe in his case, 10 eV of electron recoil corresponds to a different dark matter mass. Okay? And how do you know? Well, my detect the quenching factor is different. But it does matter? Yeah, it does matter. Because then we go back to this one again, to the minimum velocity, and say, okay, if I move the dark matter mass around, you are increasing or decreasing the probability of finding of the particle. They have different velocity distributions. You see? So it's not trivial to claim something if you just measure how many electrons or how many phonons you detect. The way you convert back to a nuclear recoil energy depends on what your detector is made of. Okay? And I need to go. Man, there's so much I need to cover. And we need to go. So I still need to cover xenon-based detectors. I'm going to cover in the next lecture. Okay, guys, we are done for today. I'm late to pick up my girls. and see you all on Monday at 10 a.m. Bye. Desliguei assim. Fala pro pessoal que as 2 horas tem a defesa do Maurício.
Ok.
Aí eu sinto. Tchau.
Tchau. 2 horas tem a defesa do Maurício.
Espera. É às 2 ou é às... Sim?
Gravando, tá gravando.
Só um momento.
A que hora é a defesa? Ele não me falou.
2 horas.
Ah, tá. Tchau.
Tchau, tchau.